Hello, I am Austin Stoker. My partner is Giovanni Jean, and we are here to present Project 6 for Material Science. The grain structure of the cold silver alloy looks very different in a fast quenched and a slow cooled state. So we'll first start with the fast quenched state, where that will form very small grains because the material does not have time to grow very large grains, so it is going to form very small, tightly packed grains in a cord structure. And in a slowly cooled version of this material, you're going to get much larger grains, very long grains, because the material is going to be cooling for a longer time. So these grains have a long time to form. And they're going to form in an equilibrium type of structure, as you can see here. Now we're given 1 kilogram of this gold-silver alloy that is 40% weight gold. We're going to cool it from 1200 degrees Celsius to 1000 degrees Celsius, and we are going to examine the phases that are present, the mass of each phase, and the gold mass portions of each phase. So here we have the gold-silver phase diagram. And in this problem, we are given a 40% concentration of gold at a temperature of 1000 degrees. So we're going to start at 40 and go all the way up to 1000 degrees. And that is going to be right here. And so we are in a state where we are liquid and solid. So now we're going to move our line over towards the liquidus and measure the concentration there. And the concentration at this point is 35%. And then when we move our tie line over to alpha, or to the solidus, we are going to have a concentration of about 47%. We're going to use those concentrations to help determine the weight of our gold and silver, and the weight of the liquid and the solid that is in this material. And this material is going down in this process from 1200, which is above this graph even, so it is going to start as a liquid, and it's going to drop all the way down to 1000, which is down here. So we're going to start as a liquid and drop all the way down, and we're going to end up being part liquid, part solid, and we're going to determine what percentages of liquid and solid that we have. To determine the mass of each phase, I used these equations right here and used the corresponding concentration values that we determined from the graph on the previous slide. And this comes out to a mass of liquid as 0.58 kilograms and a mass of solid of 0.42 kilograms, which adds up to 1 total kilogram. Now, using those two masses, the liquid and the solid, we are able to determine the mass of liquid and solid gold and silver. And so, going through this chart that we have here, you have, first we'll start with gold. You start with 0.58 kilograms for gold and silver, because that is what you have for liquid. And then your percentage of liquid gold, in this case, is going to be 0.35, because that is the percent liquid where on the tie line, when you move left and go to the liquidus, that was the percent or the concentration of liquid that we had for gold. So we're going to multiply those two together, and you're going to get 0.203 kilograms. And then the same thing is going to happen for silver, except it's going to be the opposite. You're going to have 0.65% of silver. and that will give you 0.377 kilograms. And now your solid, you'll do the same thing. We have 0.42 kilograms of solid material in this alloy, and you're going to multiply that by 0.47 because that is our concentration of solid that we found from the graph. And then with your silver, you're going to multiply it by 0.53 because you have the opposite. And so you get these values here, and then to find, or then adding up your value of liquid silver and solid silver, you get around 0.4 kilograms, which is what we started with, is 0.4 kilograms. This was the percentage, or 40% of percent weight for the gold. And then you would also get around 0.6 kilograms of silver, which adds up and would make sense here.
Mimicking brain memory. Gold silver alloy can form conductive filaments inside a thin insulating layer when an electric field is applied. It can switch between high and low resistance states. This mimics how neurons fire in the brain. So now I present the question. What if we introduce another alloy, like copper nickel? Copper nickel, or the same gold silver we've been going with? Which is better to mimic those brain, more specifically those neurons firing? And it would be our first example, gold silver alloy, because these reasons. The high ion mobility of Ag, thermodynamic stability and consistent oxidation behavior, less electromigration fatigue, and low energy consumption. All right, now I'll try and get the density of both gold and silver. Both gold and silver are FCC, face center cubic. Face center cubic refers to a type of unit cell. The unit cell is the smallest repeating unit in a crystalline lattice structure and is measured in nanometers. All right, the following are the governing equations in relation to density and face center cubic. First, you have A, which is equal to R, should be 4R, sorry about that, divided by the square root of 2. V, which is A cubed. M, which is 4 times capital M over NA. And finally, you get density, which is rho is equal to M over V. And looking at our key here, we can see what that really means. We get the lattice parameter by using the atomic radius, which we also use to get the volume. And in terms of mass per unit cell, we get that from the atomic mass and Avogadro's constant. All right, so there are 3 variables we need in order to solve this problem. So the first one we already know, just from looking at the periodic table, is 196.967 grams per mole. That is big M. The second and third is Avogadro's constant, which is just an unknown constant to be given, and R, which is 0.146 nanometers, which I got from Princeton. All right, given all the information we need, we can finally solve this problem. For A, I got 0.413 times 10 to the 9 meters, and then we cube that, and then you should get 0.0704 nanometers cubed. I chose to leave it nanometers cubed for simplicity, but it does not impact my data at all. For M, I got 1.308 times 10 to the negative 24 kilograms per mole. I made sure to convert into kilograms. And finally, for density, M over V, I got 1.858 times 10 to the 5 kilograms per meter cubed. Following a similar process than what we did for the gold, we got it A is equal to 4.073 times 10 to the negative 10. You cube that, and you should get 67.568 times 10 to the negative 30, which would be our volume. And for our mass, I got a value of 7.165 times 10 to the negative 25. All right, you put one over the other, and you should get left with your density, which is 106 times 10 to the 4 kilograms per meter cubed.